95% of the universe is made up of something we can't see, can't touch, and barely understand. Dark matter and dark energy, these invisible forces shape everything around us, yet they remain one of the greatest mysteries in science. What's even more astonishing is that the cosmos, with all its stars, galaxies, and swirling nebulae, makes up just a tiny fraction of what's out there. The rest, it's a puzzle we're still trying to solve. Today, we're diving into the unknown, exploring 50 unanswered questions about the cosmos that will not only amaze you, but also challenge everything you think you know about existence. From the bizarre behavior of black holes to the possibility of parallel universes, each question peels back another layer of the universe's secrets. Why do these questions matter? Because they push the boundaries of human knowledge, inspire generations of scientists, and remind us just how much we still have to discover. As we journey through these cosmic mysteries together, you'll encounter mind-blowing facts, intriguing theories, and questions that might just keep you up at night. So, are you ready to explore the universe's greatest unknowns? Let's dive in. Picture the universe as a vast, intricate tapestry, woven with threads of light, gas, and galaxies. But here's the twist: nearly 1/3 of that tapestry is invisible to us. This unseen fabric is dark matter, a mysterious substance that makes up about 27% of the cosmos. Yet, despite its overwhelming presence, it refuses to reveal itself directly. We can't see it, touch it, or detect it with our current technology. So how do we even know it exists? The answer lies in the way it interacts with the universe around it. Through gravity, galaxies spin faster than they should if only the visible matter were holding them together. Stars on the outer edges of galaxies move at speeds that defy the laws of physics as we understand them, suggesting something invisible is exerting a gravitational pull. This is where dark matter steps in, or rather, where its presence is felt. It's like trying to solve a puzzle where most of the pieces are missing, yet their shape is revealed by the empty spaces they leave behind. Scientists have proposed several theories to explain what dark matter might be. One leading idea involves WIMP, weakly interacting massive particles. These hypothetical particles are thought to be massive enough to exert gravitational influence, but so elusive that they rarely interact with ordinary matter. Another candidate is the action, a particle so light and ghostly that it's almost impossible to detect. Yet, despite decades of searching, neither WIMP nor actions have been conclusively found. This raises a tantalizing question. Are we looking in the right places, or could dark matter be made of something entirely different, particles we haven't even imagined yet? The mystery deepens when we consider that dark matter doesn't just hide in the shadows, it shapes the very structure of the universe. Without it, galaxies wouldn't form as they do, and the cosmos as we know it wouldn't exist. It's a cosmic architect working behind the scenes, invisible yet indispensable. But as much as we've learned, we're still left wondering, what is dark matter truly made of? And how does it fit into the larger puzzle of the universe? As we ponder these questions, it's worth noting that dark matter isn't the only unseen force shaping our universe. Its counterpart, dark energy, is equally enigmatic and perhaps even more perplexing. But that's a story for the next cosmic mystery we'll explore. For now, the nature of dark matter remains one of the greatest unanswered questions in science, a reminder that even in the vastness of space, some secrets are still waiting to be uncovered. Imagine a force so powerful that it shapes the very fabric of our universe, yet remains completely invisible to us. This is the enigmatic nature of dark energy, an elusive phenomenon that makes up a staggering 68% of the cosmos. But what exactly is dark energy, and why does it hold such a pivotal role in the fate of the universe? Let's unravel this mystery. For centuries, scientists believed the universe was static, unchanging, and eternal. But in the late 1990s, observations of distant supernovae revealed something astonishing. The universe isn't just expanding, it's accelerating. This groundbreaking discovery turned our understanding of cosmology on its head. Something was pushing galaxies apart faster and faster, and that something was named dark energy. So, what could dark energy be? One leading idea ties it to Albert Einstein's cosmological constant, a term he once introduced and later dismissed to explain a static universe. Today, it's seen as a possible representation of dark energy, suggesting that empty space itself has an inherent energy that drives expansion. But here's the twist: if dark energy is a property of space, why does it behave so differently from everything else we know? Alternative theories like quintessence propose that dark energy might not be constant at all. Instead, it could be a dynamic field that changes over time, adding another layer of complexity to this cosmic puzzle. Could dark energy evolve, or is it truly unchanging? We still don't know. Yet, the most profound question remains: is dark energy a fundamental property of the universe, or is it something entirely beyond our current understanding? Could it be a sign that we're missing a critical piece of the cosmic puzzle? As we ponder these questions, we're reminded of how much remains to be discovered. And speaking of discovery, this leads us to another mind-bending mystery: the origins of the universe itself. How did everything we see and everything we can't see come into existence? Let's journey back to the very beginning, to a moment when the universe was smaller than a single atom, and explore the story of the Big Bang. The Big Bang is often described as the moment when everything began, but what exactly sparked it? This question lies at the heart of one of the most profound mysteries in cosmology. According to the Big Bang theory, the universe exploded into existence nearly 13.8 billion years ago from an infinitely dense and hot state known as a singularity. But what caused this singularity to erupt, and what, if anything, existed before it? These questions challenge our understanding of physics and push the boundaries of human knowledge. A singularity, by definition, is a point where the laws of physics as we know them break down. Gravity becomes infinitely strong, and space-time curves into an unfathomable state. This makes it nearly impossible to study or even conceptualize what happened at that exact moment. Some scientists suggest that quantum fluctuations, tiny, random changes in energy, might have played a role in triggering the Big Bang. These fluctuations, which occur even in the vacuum of space, could have provided the initial spark that set the universe in motion. But this is just one piece of a much larger puzzle. Another intriguing possibility is the multiverse theory, which proposes that our universe is just one of many in a vast cosmic landscape. In this scenario, the Big Bang might not have been a unique event, but rather one of countless similar explosions across an infinite expanse of reality. This idea leads to even more questions. Could the Big Bang be part of a cyclical process, with universes expanding, collapsing, and reborn in an endless loop? Or was it a one-time event, a singular moment of creation that set the stage for everything we see today? As we ponder these theories, one thing becomes clear: the Big Bang isn't just the beginning of our universe, it's a doorway to even deeper mysteries. What existed before it? Was there truly nothing, as we often imagine? Or is the concept of before even relevant when discussing the birth of space and time? These questions take us to the edge of what we can comprehend, blending science with philosophy and leaving us in awe of the cosmos. And as we stand on this precipice of understanding, it's worth asking, could the answers lie not just in the moment of the Big Bang, but in the fabric of reality itself? What if the universe holds clues to its own origins, hidden in the stars, galaxies, and even the empty voids that stretch across the cosmos? The journey to uncover these truths is far from over, and each discovery brings us closer to unraveling the ultimate mystery of existence. But what if we could rewind the cosmic clock even further? What existed before the Big Bang? This question takes us into one of the most speculative and mind-bending areas of cosmology. The Big Bang is often described as the beginning of everything: time, space, and matter. But what lies beyond that singularity? Was there truly nothing, or does the universe have a deeper origin story waiting to be uncovered? One intriguing idea is the Big Bounce theory, which suggests that our universe might be part of an endless cycle of expansion and contraction. Picture this: instead of a single explosive beginning, the Big Bang could have been the result of a previous universe collapsing in on itself, only to rebound and give birth to our cosmos. It's a cosmic reset button, with each cycle leaving faint traces of the one before it. Then there's the concept of eternal inflation, where our universe is just one bubble in a vast, ever-expanding multiverse. Imagine an infinite ocean of space, where new universes constantly pop into existence like bubbles in a fizzy drink. Each of these universes could have its own unique laws of physics, making our reality just one of countless possibilities. And at the very foundation of this multiverse lies the idea of quantum foam, a chaotic, seething sea of energy where universes might spontaneously emerge and vanish in the blink of an eye. But here's the real kicker: does the word "before" even make sense when we're talking about the Big Bang? If time itself began at that moment, then the concept of something happening before might be meaningless. It's like trying to ask what's north of the North Pole. The question itself might not have an answer within the framework we understand. As we ponder these theories, one thing becomes clear: the universe is far stranger and more mysterious than we can imagine. And while we don't yet have all the answers, the journey to uncover them is nothing short of thrilling. So, if the universe had a beginning, what does that mean for its ultimate fate? Will it expand forever, or could it one day collapse back in on itself? Let's explore that next. What lies at the end of the universe? Will it fade into a cold, silent void, or will it collapse in on itself in a cataclysmic finale? These are the questions that haunt cosmologists as they try to predict the ultimate fate of the cosmos. Two leading theories dominate this cosmic debate: the heat-death of the universe and the Big Crunch. The heat-death scenario paints a picture of an ever-expanding universe where galaxies drift farther and farther apart, stars burn out, and black holes evaporate over unimaginable timescales. Eventually, the universe becomes a vast, dark expanse devoid of energy or structure, where even time itself loses meaning. It's a chilling thought: a cosmos that ends not with a bang but with a whisper. On the other hand, the Big Crunch offers a dramatically different ending. In this scenario, the expansion of the universe slows, stops, and eventually reverses. Galaxies, stars, and even atoms would be pulled back together, collapsing into a single point, a cosmic singularity. This fiery implosion would be the opposite of the Big Bang, a violent crescendo to the universe's story. But what determines which of these fates awaits us? The answer lies in the mysterious force known as dark energy. This invisible energy permeates space and drives the accelerated expansion of the universe. If dark energy continues to dominate, the universe will likely expand forever, leading to heat death. But if dark energy weakens or changes over time, gravity could regain control, pulling everything back together in a Big Crunch. The question remains: will the universe end in silence or in fire? While we can't yet predict with certainty, the search for answers is reshaping our understanding of reality. And speaking of reality, what if our universe isn't the only one out there? What if there are parallel universes, each with its own laws of physics and its own ultimate fate? That's a mystery we'll explore next. What if everything you've ever done or could have done exists somewhere out there in a completely different reality? That's the mind-bending idea behind parallel universes, a concept that suggests our universe might just be one of countless others. Think of it like this: every choice you've ever made, from what you ate for breakfast to the career you pursued, could have played out differently in another version of existence. These alternate realities, often grouped under the umbrella of the multiverse, aren't just science fiction. They're serious scientific theories that challenge our understanding of reality itself. One of the leading ideas supporting the multiverse comes from string theory, which proposes that our universe is just one of many bubbles floating in a vast cosmic foam. Each bubble could have its own unique set of physical laws, meaning that in one universe gravity might be stronger, while in another time could flow backward. Another fascinating theory suggests that every decision we make creates a branching path, spawning an entirely new universe where the opposite choice was made. It's like a cosmic game of what if, where every possibility plays out somewhere in the multiverse. But here's the real question: if these parallel universes exist, could we ever detect them? Some scientists believe that faint imprints of other universes might be hidden in the cosmic microwave background radiation, the afterglow of the Big Bang. Others speculate that gravitational waves or quantum entanglement could hold clues. Yet, even if we found evidence, could we ever interact with these alternate realities? The answer remains elusive, but the possibility alone sparks endless curiosity and wonder. This leads us to another profound mystery: the nature of time itself. If parallel universes exist, does time flow the same way in all of them? Or could time be a flexible, multidimensional fabric that connects these realities in ways we can't yet comprehend? The exploration of parallel universes doesn't just challenge our understanding of space, it forces us to rethink the very fabric of existence. And as we ponder these questions, we're reminded that the cosmos is far stranger and more mysterious than we could ever imagine. What if everything we think we know about time is wrong? At first glance, time seems straightforward. It's the ticking clock, the rising sun, the changing seasons. But dig a little deeper, and you'll find that time is one of the most mysterious and debated concepts in both science and philosophy. Albert Einstein revolutionized our understanding of time with his theory of relativity, showing that it's not a fixed, unchanging backdrop to the universe. Instead, time is relative, bending and stretching depending on how fast you're moving or how close you are to a massive object like a black hole. Imagine two people, one speeding through space on a rocket, the other standing still on Earth. For the astronaut, time would pass more slowly compared to the person on the ground. This isn't science fiction, it's a proven reality confirmed by countless experiments. But what if time isn't even real in the way we experience it? Enter the block universe theory, a mind-bending idea that suggests past, present, and future all exist simultaneously. Think of the universe as a giant loaf of bread, where each slice represents a moment in time. From this perspective, everything that has ever happened or will happen is already out there in the cosmic loaf. Your birth, your first steps, even the distant death of the universe, they're all just different slices of the same loaf. This raises a profound question. Is time a fundamental property of the cosmos, or is it simply a way for our brains to make sense of the world? Some scientists argue that time might be an illusion, a construct created by our consciousness to navigate reality. And then there's the tantalizing possibility of time travel. If the block universe theory is correct, could we ever find a way to move between those slices of time? While science fiction has explored this idea for decades, real-world physics offers intriguing possibilities like wormholes or cosmic strings that might one day make time travel a reality. But for now, these ideas remain firmly in the realm of theory, leaving us to wonder, What secrets about time are still waiting to be uncovered? As we peel back the layers of this cosmic mystery, we're reminded that the universe is far stranger and more wonderful than we could ever imagine. What if you could step into a time machine and travel to the past or future? It's a concept that has fascinated humanity for centuries, fueling countless stories and scientific debates. But is time travel actually possible, or is it just the stuff of science fiction? Let's dive into the theoretical foundations that make this idea so intriguing and so puzzling. One of the most compelling theories about time travel involves wormholes, hypothetical tunnels through space-time that could connect two distant points in the universe. Imagine folding a piece of paper so that two points touch. A wormhole would be like poking a hole through that fold, creating a shortcut. While wormholes are mathematically possible according to Einstein's theory of general relativity, they'd require exotic matter with negative energy to stay open, something we've yet to discover. Then there's the idea of closed time-like curves, paths through space-time that loop back on themselves, effectively allowing an object or person to return to their own past. These curves are also rooted in Einstein's equations, but they come with a major catch: the grandfather paradox. What happens if you go back in time and prevent your own existence? The paradox challenges the very logic of time travel, leaving scientists to ponder whether the universe would somehow prevent such contradictions or if alternate timelines could exist. But here's where things get even more mind-bending. On a quantum level, experiments suggest that particles might already be time-traveling. In certain conditions, particles seem to defy the usual flow of time, behaving in ways that hint at backward movement at the subatomic scale. While this doesn't mean humans could hop into a quantum time machine anytime soon, it does open the door to fascinating possibilities about how time works at its most fundamental level. So, could humans ever harness time travel? The answer remains shrouded in mystery. While the math allows for the possibility, the practical challenges like finding exotic matter or navigating paradoxes are monumental. It's a tantalizing question that keeps scientists and dreamers alike searching for answers. And speaking of mysteries, let's turn our attention to one of the cosmos' most enigmatic phenomena: black holes. What secrets do they hold, and how might they reshape our understanding of time and space? Black holes are among the most mysterious and awe-inspiring phenomena in the universe. Imagine a place where gravity becomes so intense that it warps space and time to the point where nothing, not even light, can escape its pull. This boundary, known as the event horizon, marks the point of no return. But what lies beyond it? At the heart of a black hole lies the singularity, a point where the laws of physics as we know them break down entirely. Here, matter is crushed into an infinitely dense state, and our understanding of reality reaches its limits. One of the biggest puzzles surrounding black holes is the information paradox. According to quantum mechanics, information about the particles that fall into a black hole should never be destroyed. But if that information is trapped forever inside the black hole, how does it escape? This paradox has sparked groundbreaking theories like Hawking radiation, which suggests that black holes aren't completely black after all. Over unimaginable timescales, they can slowly evaporate, releasing energy and possibly the information they once consumed. Another fascinating idea is the holographic principle, which proposes that all the information about what falls into a black hole is encoded on its event horizon like a cosmic hologram. This theory blurs the line between 2 dimensions and 3, suggesting that our perception of reality might be far more complex than we realize, but the mysteries don't stop there. Could black holes be gateways to other universes? Some theories speculate that they might connect to parallel realities, while others argue they're simply cosmic dead ends where matter and energy meet their final fate. As we ponder these questions, another cosmic enigma comes into view: white holes. If black holes are regions where everything is pulled in, white holes are theorized to be the opposite, regions where matter and energy are expelled. While black holes have been observed indirectly, white holes remain purely theoretical. Could they exist, or are they just a mathematical curiosity? This brings us to the next chapter in our cosmic journey, where we'll explore the possibility of white holes and what they might reveal about the fabric of the universe. What if the universe has a cosmic reset button? Enter white holes, theoretical opposites of black holes. While black holes are known for their insatiable appetite, pulling in everything that crosses their event horizon, white holes are thought to do the exact opposite. They spew out matter and energy, refusing to let anything in. But do they actually exist, or are they just a fascinating idea born from the equations of theoretical physics? White holes emerge as solutions to Einstein's field equations, the same mathematical framework that predicts black holes. But unlike their dark counterparts, white holes remain purely theoretical. They've never been observed, and their existence would defy some of the fundamental laws of physics we currently understand. For instance, they would require time to run backward, which raises all sorts of mind-bending questions about causality and the nature of the universe. One intriguing possibility is that white holes could be connected to black holes through wormholes, hypothetical tunnels in space-time. Imagine a black hole swallowing matter on one end and a white hole ejecting it out somewhere else in the cosmos. This idea sparks endless speculation. Could white holes be the source of mysterious cosmic phenomena like gamma-ray bursts or even the Big Bang itself? Some scientists have even proposed that our universe might have emerged from a white hole in a previous collapsed universe. Yet, as tantalizing as these ideas are, the reality is that white holes remain shrouded in mystery. Without observational evidence, they live in the realm of what if, challenging our understanding of physics and the cosmos. But that's the beauty of theoretical physics. It pushes us to think beyond what we know and explore the boundaries of possibility. And speaking of boundaries, this idea of connections between black holes and white holes leads us to another fascinating concept: wormholes. Could these cosmic shortcuts be the key to traversing vast distances in the universe? Let's dive into that next. What if the vast distances between stars and galaxies weren't as insurmountable as they seem? Enter wormholes, cosmic shortcuts that could, in theory, bend the fabric of spacetime itself, creating tunnels that connect distant corners of the universe. These hypothetical structures, predicted by Einstein's theory of general relativity, have long fascinated scientists and storytellers alike. But are they just the stuff of science fiction, or could they one day become a reality? At their core, wormholes are thought to be bridges between 2 points in spacetime, potentially allowing travel across unimaginable distances in the blink of an eye. Picture folding a piece of paper so that 2 points touch. Now imagine a tunnel piercing through that fold. That's the basic idea behind a wormhole. But here's the catch. While the math suggests they could exist, creating or stabilizing one is a whole different story. Wormholes, as we understand them, would require an enormous amount of energy, possibly even exotic matter with negative energy density, to keep them from collapsing instantly. And so far, we have no evidence that such matter exists. In science fiction, wormholes have become a staple of interstellar travel, appearing in everything from Interstellar to Star Trek. They offer a tantalizing vision of humanity exploring the cosmos without the constraints of time and distance. But in reality, the challenges are staggering. Even if we could create a wormhole, navigating it safely would be a monumental task. The intense gravitational forces could tear anything apart, and the stability of such a structure remains a mystery. So, could wormholes ever be used for practical space travel? The answer, for now, lies somewhere between hope and speculation. While they remain a fascinating theoretical possibility, the technological and scientific hurdles are immense. Still, the idea of wormholes reminds us of the boundless creativity of the human mind and our enduring desire to explore the unknown. As we ponder whether wormholes could one day unlock the secrets of the universe, another profound question arises. How did life itself begin in the vast expanse of space? The origins of life remain one of the greatest mysteries of all, inviting us to explore the cosmic building blocks that make existence possible. One of the most profound questions humanity has ever asked is this: are we alone in the universe? The search for extraterrestrial life isn't just a topic for science fiction, it's a real scientific endeavor that challenges our understanding of biology, chemistry, and the very nature of existence. To even begin answering this question, we need to consider the conditions necessary for life as we know it. Water, organic molecules, and a stable environment are often seen as the building blocks. But could life exist in forms we can't even imagine, thriving in environments that would seem hostile to us? This brings us to the search for habitable exoplanets, worlds orbiting other stars that might have the right ingredients for life. Astronomers have discovered thousands of these planets, some within the so-called Goldilocks zone, where temperatures are just right for liquid water to exist. But finding a potentially habitable planet is only the first step. The real challenge lies in detecting signs of life, whether it's the faint traces of oxygen in an atmosphere or the presence of complex molecules that hint at biological activity. To frame this search, scientists often turn to the Drake equation, a fascinating tool that estimates the number of active, communicative extraterrestrial civilizations in our galaxy. The equation considers factors like the rate of star formation, the fraction of stars with planets, and the likelihood of life developing on those planets. While the Drake equation doesn't give us a definitive answer, it helps us think critically about the possibilities and the uncertainties involved in the search for life beyond Earth. But here's the puzzling part. If the universe is so vast and the conditions for life seem so widespread, why haven't we found any evidence of extraterrestrial intelligence? This is the heart of the Fermi paradox. With billions of stars and planets in our galaxy alone, the odds suggest that intelligent life should have emerged somewhere else by now. So where is everyone? Could advanced civilizations be too far away or perhaps too different for us to recognize? Or is there something about the nature of life itself that makes it incredibly rare, even in a universe as immense as ours? As we ponder these questions, one thing becomes clear. The search for extraterrestrial life isn't just about finding aliens, it's about understanding our place in the cosmos. And as we turn our gaze to the stars, we can't help but wonder, what kind of intelligence, if any, might be looking back at us? If the universe is so vast with billions of galaxies and trillions of stars, why haven't we found any signs of intelligent life beyond Earth? This question lies at the heart of the Fermi paradox, a puzzle that has baffled scientists and thinkers for decades. Named after physicist Enrico Fermi, who famously asked, "Where is everyone?" The paradox highlights the contradiction between the high probability of extraterrestrial civilizations existing and the complete lack of evidence for their existence. One of the most compelling explanations is the concept of the Great Filter. This idea suggests that at some point in the development of life, whether it's the emergence of life itself, the evolution of intelligence, or the ability to create advanced technology, there's a barrier so immense that most civilizations never surpass it. If this filter lies in our past, we might be extraordinarily lucky to have made it this far. But if it's in our future, it could mean that civilizations like ours are doomed to self-destruct before they can colonize the stars. Another possibility is that intelligent life is simply exceedingly rare. The conditions needed for life to arise, evolve, and develop advanced technology might be so specific that Earth is one of a kind. Or perhaps advanced civilizations exist, but they're so far away that communication or detection is impossible with our current technology. Imagine trying to spot a single candle on a distant planet. Our tools might not yet be sensitive enough to find them. Then there's the idea that alien life might be so different from us that we don't even recognize it as life. What if their methods of communication or their forms of technology are beyond our comprehension? They could be sending signals we can't detect or building structures we can't see. But perhaps the most profound question is this: are we truly alone, or is the universe teeming with life that we simply can't perceive yet? This mystery leads us to another profound idea: the nature of consciousness itself. Could it be that intelligence and awareness are common in the cosmos, but expressed in ways we can't yet understand? As we ponder the silence of the stars, we're left to wonder not just about the existence of others, but about the very essence of what it means to be alive in this vast, mysterious universe. When we think about consciousness, we often assume it's something uniquely tied to life on Earth, a product of complex brains and biological systems. But what if consciousness isn't just a human trait or even an earthly one? What if it's woven into the very fabric of the cosmos? This idea might sound like science fiction, but some scientists and philosophers are seriously considering it. Theories like panpsychism propose that consciousness isn't something that emerges solely from brains. It's a fundamental property of the universe itself, as basic as space, time, or energy. Imagine this: every particle, every star, and every galaxy might possess some form of awareness, no matter how rudimentary. It's a radical thought, but it raises fascinating questions. If consciousness is universal, could it mean that life elsewhere in the cosmos is not just possible, but inevitable? And if the universe itself has some form of awareness, what does that say about the nature of reality? Are we, as conscious beings, just one small part of a much larger, interconnected system? This idea doesn't just challenge our understanding of life, it reshapes how we see existence itself. It blurs the line between the physical and the metaphysical, suggesting that the universe might not just be a cold, mechanical place, but something far more dynamic and alive. And if that's true, what does it mean for our search for extraterrestrial intelligence? Could we be looking for life in all the wrong ways because we're limited by our Earth-centric view of consciousness? These questions lead us to another profound mystery: the strange world of quantum mechanics. At the smallest scales, particles behave in ways that defy our everyday understanding of reality. They can exist in multiple states at once, or instantly influence each other across vast distances. Some scientists even speculate that consciousness might play a role in shaping these quantum phenomena. Could the universe's awareness, if it exists, be influencing the very fabric of reality at the quantum level? The connection between consciousness and quantum mechanics is still a puzzle, but it's one that could unlock some of the deepest secrets of the cosmos. Imagine a world where the rules of reality as we know them no longer apply, where particles can exist in two places at once, communicate instantaneously across vast distances, and even change their behavior simply because we're watching. This isn't science fiction. This is the bizarre, mind-bending realm of quantum mechanics. At the heart of this strange universe lies a question that has puzzled scientists and philosophers for decades. What is reality, really? Let's start with the double-slit experiment, a cornerstone of quantum physics. When particles like electrons are fired at a barrier with two slits, they don't behave as you'd expect. Instead of passing through one slit or the other, they seem to pass through both simultaneously, creating an interference pattern on the other side. But here's where it gets even weirder. If you try to observe which slit the particle goes through, it stops behaving like a wave and starts acting like a single particle. This is the observer effect in action, the idea that the act of observation itself can alter the outcome of an experiment. This raises a profound question. Is reality inherently uncertain, or do we simply lack the tools to see it clearly? Some scientists argue that particles don't have definite properties until they're measured, a concept central to the Copenhagen interpretation of quantum mechanics. According to this view, the universe is a probabilistic playground, and reality only solidifies when observed. But not everyone agrees. The many worlds theory, for instance, suggests that every possible outcome of a quantum event actually happens, branching off into parallel universes. In this interpretation, reality isn't uncertain, it's just infinitely vast. So, what does this mean for our understanding of the cosmos? If particles can be entangled, connected in such a way that the state of one instantly influences the state of another, no matter the distance, could the universe itself be a vast, interconnected web? And if the very act of observation shapes reality, does that mean consciousness plays a role in the fabric of existence? These questions don't just challenge our understanding of physics, they force us to rethink the nature of reality itself. And as we ponder the mysteries of quantum mechanics, another enigma looms large, one that governs the very structure of the universe, gravity. What is it really, and why does it hold such sway over everything from the tiniest particles to the largest galaxies? We've all felt the pull of gravity, whether it's keeping us grounded on Earth or sending an apple tumbling from a tree. But here's the twist. Gravity is actually the weakest of the four fundamental forces in the universe. Think about it. A tiny magnet can lift a paperclip, overcoming the gravitational pull of an entire planet. Yet, despite its weakness, gravity is the force that shapes galaxies, bends light, and holds the cosmos together. It's a paradox that has puzzled scientists for centuries. How can something so feeble on a small scale wield such immense power across the universe? The story of gravity takes a fascinating turn with Einstein's theory of general relativity. Here, gravity isn't just a force, it's the curvature of spacetime itself. Massive objects like stars and planets warp the fabric of the universe, creating the gravitational effects we observe. This theory has stood the test of time, explaining everything from the orbit of Mercury to the bending of light around massive objects. But when we zoom into the quantum world, gravity's story gets murky. At this tiny scale, the other forces, electromagnetism, and the strong and weak nuclear forces play by the rules of quantum mechanics. Gravity, however, refuses to fit into the same framework. It's like gravity speaks a completely different language, and scientists have been struggling for decades to find a translator. This incompatibility has led to some of the most ambitious theories in modern physics, like quantum gravity and string theory. Quantum gravity attempts to describe gravity using the principles of quantum mechanics, while string theory suggests that the fundamental building blocks of the universe are tiny, vibrating strings. These theories even propose the existence of extra dimensions, hidden layers of reality, that could explain why gravity behaves so differently from the other forces. But here's the big question. Will we ever find a unified theory that bridges the gap between gravity and quantum mechanics? The answer could reshape our understanding of the universe itself. And speaking of extra dimensions, this idea opens up a whole new realm of possibilities. What if gravity's weakness is a clue that it's leaking into dimensions we can't see? Could these hidden dimensions hold the key to unlocking the secrets of the cosmos? As we dive deeper into these questions, the mysteries of gravity only seem to grow more profound, reminding us just how much we still have to discover about the forces that shape our reality. What if the universe is far more complex than we can see or touch? beyond the three dimensions we navigate every day, length, width, and depth, scientists speculate that there may be hidden dimensions curled up so tightly that they escape our notice. This isn't science fiction, it's a cornerstone of string theory, which suggests the universe could have as many as 10 or 11 dimensions. These extra dimensions might be compactified or folded in on themselves at scales so small that even our most advanced instruments can't detect them. But why would the universe need more dimensions than the ones we're familiar with? One compelling idea is that these hidden dimensions could hold the key to understanding some of the greatest mysteries in cosmology, like dark matter and dark energy. Dark matter, which makes up about 27% of the universe, doesn't interact with light, making it invisible to us. Dark energy, on the other hand, is the mysterious force driving the accelerated expansion of the universe. Could these phenomena be linked to particles or forces existing in these extra dimensions, leaking into our three-dimensional world in ways we can't yet comprehend? The challenge, of course, is proving their existence. If these dimensions are so small, perhaps a billionth of the size of an atom, how could we ever detect them? Some theories suggest that high-energy experiments, like those conducted in particle colliders, might reveal subtle clues. For example, if particles were to momentarily disappear into these dimensions, it could create anomalies in our observations. But so far, no definitive evidence has been found. This leads to an even bigger question. Could we ever interact with these extra dimensions? Imagine a world where we could access them, unlocking entirely new realms of physics and technology. While it sounds like the stuff of dreams, the possibility reminds us just how much we still don't know about the cosmos. And as we ponder these hidden layers of reality, we're led to another profound mystery, one that's been with us since the dawn of science itself, the nature of light. What is it really, and how does it behave in ways that continue to baffle and inspire us? Light has always been one of the most fascinating enigmas in the cosmos. Is it a particle, a wave, or something else entirely? For centuries, scientists debated this question, and the answer turned out to be far stranger than anyone could have imagined. Light behaves as both a particle and a wave, a phenomenon known as wave-particle duality. This dual nature was first glimpsed through the photoelectric effect, where light striking a material ejects electrons acting like discrete particles. Yet, light also exhibits wave-like properties such as interference and diffraction, as seen in experiments like the double-slit setup. These experiments left physicists puzzled. How could light be both at once? The implications of this duality stretch far beyond light itself, providing a cornerstone for quantum mechanics. At the quantum level, particles don't behave like the solid, predictable objects we're used to. Instead, they exist in a blurry state of probabilities, only revealing their true nature when observed. Light, as both particle and wave, challenges our intuitive understanding of reality. It raises profound questions. Is light truly both, or is it something beyond our current comprehension? Could it be that our limited perspective prevents us from seeing the full picture? This duality isn't just a quirk of light. It's a window into the bizarre and beautiful world of quantum physics, where the rules of the macro world no longer apply. It forces us to rethink what we know about the universe and our place within it. And as we ponder these questions, we're reminded that even something as fundamental as light holds secrets waiting to be unraveled. Speaking of cosmic mysteries, let's shift our gaze to another profound puzzle, the cosmic microwave background. This faint glow, a relic from the early universe, offers clues about the birth of everything we see today. But what does it tell us, and why is it so crucial to our understanding of the cosmos? That's a story for the next section. Imagine holding a photograph of the universe when it was just a baby less than 400,000 years old. That's essentially what the cosmic microwave background, or CMB, is. a faint, ancient glow that permeates the cosmos, a relic from the Big Bang itself. This afterglow is the oldest light we can observe, a cosmic snapshot frozen in time from when the universe transitioned from a hot, dense soup of particles to a cooler, more transparent state. It's like finding a time capsule buried billions of years ago, and it's one of the most compelling pieces of evidence we have for the Big Bang theory. But the CMB isn't just a static image of the past, it's a treasure trove of information. Tiny fluctuations in its temperature, often compared to the texture of an orange peel, reveal the seeds of all the structures we see today: galaxies, clusters, and even the vast cosmic web. These fluctuations are echoes of the quantum ripples that existed in the early universe, stretched and amplified over billions of years. Without them, the universe might have remained a featureless void, devoid of the complexity we see today. Yet, as much as the CMB has helped us understand the origins of the cosmos, it also presents puzzles that challenge our understanding. For instance, there's the curious case of the cold spot, a region in the CMB that's significantly cooler than its surroundings. Some theories suggest it could be evidence of a collision with another universe, while others propose it's just a statistical fluke. Then there's the mystery of the CMB's large-scale anomalies, patterns and asymmetries that don't quite fit our models. Could these be clues to new physics, or are they simply artifacts of how we observe the universe? What's even more fascinating is that the CMB still holds secrets we've yet to uncover. It's like a cosmic puzzle with missing pieces, waiting for sharper observations and more advanced technologies to reveal its hidden truths. What might we learn about inflation, dark energy, or even the multiverse by decoding its subtle signals? The answers could reshape our understanding of the universe's birth and evolution. And speaking of cosmic puzzles, let's turn our attention to another enigmatic player in the universe: neutrinos. These ghostly particles, which barely interact with matter, are another window into the early universe. What can they tell us about the moments just after the Big Bang, and how do they fit into the grand cosmic puzzle? Imagine a particle so elusive that it can pass through an entire planet without leaving a trace. That's the neutrino, often called the ghost particle of the universe. These tiny, nearly massless particles are produced in enormous quantities during nuclear reactions, like those in the sun or in supernova, yet they barely interact with matter. In fact, trillions of neutrinos are streaming through your body right now, completely unnoticed. Their ability to slip through solid objects as if they weren't even there makes them one of the most mysterious and fascinating particles in existence. Neutrinos are born in some of the most extreme environments in the cosmos. When stars fuse hydrogen into helium, or when a massive star collapses in a supernova, they release a flood of these ghostly particles. But detecting them is no easy task. Because neutrinos barely interact with matter, scientists have to build massive detectors, often buried deep underground, to catch even a handful of these particles. One of the most famous experiments, the Super Kamiokande detector in Japan, uses a gigantic tank filled with ultra-pure water to capture the faint flashes of light produced when a neutrino occasionally collides with an atomic nucleus. But the mystery of neutrinos goes even deeper. They have a strange habit of changing their flavor as they travel through space, a phenomenon known as neutrino oscillation. This means a neutrino that starts its journey as one type can morph into another type before it's detected. This discovery completely upended our understanding of particle physics, proving that neutrinos have mass even if it's incredibly tiny. It also opened up new questions about the fundamental nature of matter and the universe. Perhaps the most tantalizing question is whether neutrinos could be connected to the universe's missing mass. We know that the visible matter we see, stars, galaxies, and planets, makes up only a small fraction of the universe's total mass. The rest is dark matter, an invisible substance that exerts gravitational pull but doesn't emit light. Could neutrinos, with their ghostly presence, be part of this cosmic puzzle? While they're too light to account for all of dark matter, their behavior hints that there might be more to these particles than we currently understand. As we ponder the secrets of neutrinos, we're reminded of another enigmatic counterpart in the universe, antimatter. Just as neutrinos challenge our understanding of matter, antimatter presents its own set of mysteries, from its fleeting existence to its role in the early universe. What happens when matter and antimatter meet, and why is there so much more matter than antimatter in the cosmos? These questions lead us deeper into the heart of particle physics, where every discovery brings us closer to unraveling the universe's most profound secrets. Imagine a mirror universe where everything is the opposite of what we know. In this universe, particles have counterparts with opposite charges, a kind of cosmic twin. This isn't science fiction, it's the reality of antimatter. During the Big Bang, matter and antimatter should have been created in equal amounts. Yet, when we look around, the universe is overwhelmingly made of matter. So, where did all the antimatter go? This is one of the most profound mysteries in modern physics. Scientists believe that in the early universe, for every particle of matter, there was a corresponding particle of antimatter. When matter and antimatter meet, they annihilate each other in a burst of energy. If everything had been perfectly balanced, the universe as we know it would have annihilated itself long ago. But something tipped the scales. Somehow, matter survived and antimatter vanished into the cosmic shadows. This imbalance is called Baryon asymmetry, and it's a puzzle that has left physicists scratching their heads for decades. Experiments at places like CERN are trying to uncover the secrets of antimatter. Researchers have managed to create and trap tiny amounts of antimatter in labs, studying its properties to see if there's any clue as to why it's so rare. One theory suggests that there might have been a slight asymmetry in the laws of physics themselves, favoring matter over antimatter in the early universe. Another possibility is that antimatter is hiding somewhere in the cosmos, perhaps in regions we haven't yet observed. But why does this matter? Understanding antimatter isn't just about solving a cosmic mystery. It could help us unlock the very nature of reality, from the forces that govern particles to the origins of the universe itself. And while we're still searching for answers, the quest to understand antimatter has already led to groundbreaking discoveries, like the detection of cosmic rays, high-energy particles that rain down from space, some of which may carry traces of antimatter. Which brings us to another enigma: cosmic rays. These high-energy particles streak through space at nearly the speed of light, and their origins remain a mystery. Are they remnants of antimatter annihilations, or do they come from something even more exotic? The search for answers continues as we peer deeper into the cosmos, trying to piece together the story of how our universe came to be and why it's filled with matter, not antimatter. Now let's turn our attention to something truly extraordinary: cosmic rays. These high-energy particles racing through the cosmos at nearly the speed of light are like silent messengers from the far reaches of the universe. Every second, trillions of these particles rain down on Earth, yet their origins remain one of the most tantalizing mysteries in astrophysics. Where do they come from? What cosmic events could accelerate particles to such unimaginable speeds? And more importantly, what secrets do they hold about the universe itself? Cosmic rays are thought to originate from some of the most violent and energetic phenomena in space: supernova explosions, black holes, and even the hearts of distant galaxies. But despite decades of research, scientists still can't pinpoint their exact sources. Some theories suggest they might be produced by processes we haven't even discovered yet, hinting at entirely new physics waiting to be uncovered. Imagine that: particles traveling billions of light years, carrying clues about events so powerful they defy our current understanding of the cosmos. Detecting and studying these particles, however, is no easy task. Cosmic rays don't travel in straight lines. They're deflected by magnetic fields as they journey through space, making it nearly impossible to trace their paths back to their origins. To make matters even trickier, by the time they reach Earth, they've often broken apart, creating a cascade of secondary particles. Scientists use sophisticated detectors like the Pierre Auger Observatory in Argentina to piece together these cosmic puzzles. But even with advanced technology, the answers remain elusive. So, what could cosmic rays tell us about the universe? For one, they might hold the key to understanding dark matter, the invisible substance that makes up most of the matter in the cosmos. Some theories propose that cosmic rays could be produced when dark matter particles collide and annihilate each other. If true, studying these high-energy particles could give us our first real glimpse into the nature of this mysterious substance. And who knows, they might even reveal entirely new phenomena, something beyond our current imagination. As we ponder the mysteries of cosmic rays, it's worth noting that they're not just messengers from space. They're also a reminder of how much we still have to learn. The universe is full of wonders that challenge our understanding, pushing us to explore further and ask bigger questions. And speaking of wonders, let's shift our focus to another enigmatic phenomenon: quasars. These brilliant beacons of light powered by supermassive black holes are among the most luminous objects in the universe. What makes them shine so brightly, and what can they tell us about the early cosmos? Let's dive in and find out. Imagine an object so bright it outshines an entire galaxy, not just one, but thousands or even millions of times over. These aren't the stuff of science fiction. They're quasars, some of the most enigmatic and powerful phenomena in the cosmos. At their core lies a supermassive black hole, devouring matter at an astonishing rate. As gas and dust spiral into these cosmic monsters, they heat up to unimaginable temperatures, releasing energy that can be seen billions of light-years away. This makes quasars the brightest objects in the universe, visible even from the farthest reaches of space. But here's the real kicker: quasars aren't just fascinating because of their brilliance. They're like cosmic time capsules, offering us a glimpse into the universe's earliest days. Most quasars formed when the universe was less than 1 billion years old, a mere fraction of its current age. How did these colossal structures, powered by supermassive black holes, come into existence so quickly after the Big Bang? It's a question that baffles scientists to this day. The rapid formation of quasars challenges our understanding of how galaxies and black holes evolved in the universe's infancy. What makes quasars even more intriguing is their role in shaping the cosmos. The intense radiation they emit can influence the formation of stars and galaxies, acting like cosmic lighthouses that illuminate the dark, early universe. By studying quasars, astronomers can piece together the story of how the universe transitioned from a hot, dense soup of particles to the structured, star-filled expanse we see today. So, what can quasars tell us about the universe's beginnings? For one, they hint at the existence of supermassive black holes far earlier than we once thought possible. They also provide clues about the conditions that allowed galaxies to form and evolve. Yet, for all we've learned, quasars remain shrouded in mystery. How did these titanic black holes grow so massive so quickly? What processes ignited their incredible luminosity? As we ponder these questions, another cosmic marvel comes into focus: pulsars. Like quasars, pulsars are born from the remnants of dying stars, but their nature is entirely different. While quasars are the universe's brightest beacons, pulsars are its most precise timekeepers, spinning with astonishing regularity. But that's a story for another moment. Now, let's turn our attention to one of the most fascinating and enigmatic objects in the cosmos: pulsars. Imagine a star, not just any star, but the dense, collapsed core of a once massive sun. spinning faster than a kitchen blender and shooting out beams of radiation like a cosmic lighthouse. These are pulsars, rapidly rotating neutron stars that have captivated astronomers since their discovery in the late 1960s. What makes pulsars so remarkable? For starters, they're incredibly precise. As they spin, their beams of radiation sweep across space, and if Earth happens to be in the path of that beam, we detect a pulse of energy like clockwork. Some pulsars are so consistent that their pulses rival the accuracy of atomic clocks here on Earth. This precision makes them invaluable tools for astronomers, acting as natural cosmic clocks that help us measure time and distance across the universe with unparalleled accuracy. But pulsars aren't just timekeepers, they're also cosmic laboratories for testing the laws of physics. Their intense gravitational fields and rapid spins make them perfect for probing Einstein's theory of general relativity. When a pulsar orbits another massive object, like a black hole or another neutron star, the extreme conditions allow scientists to test predictions about how gravity warps space and time. And it doesn't stop there. Pulsars are also being used to hunt for gravitational waves, the ripples in space-time caused by cataclysmic events like merging black holes. By monitoring the timing of pulsar pulses, researchers can detect subtle changes that might reveal the presence of these elusive waves. This brings us to a tantalizing question: could pulsars hold the key to unlocking new physics? Their extreme environments challenge our understanding of matter, gravity, and even the fabric of space-time itself. Every pulse they emit carries with it the potential to reveal secrets about the universe that we've yet to uncover. And speaking of extreme cosmic phenomena, pulsars aren't the only objects in the universe that beam out intense radiation. In fact, their distant cousins, gamma-ray bursts, are some of the most energetic events in the cosmos, capable of releasing more energy in seconds than our sun will in its entire lifetime. But what causes these fleeting yet spectacular explosions? That's a mystery we'll explore next. Gamma-ray bursts are like the universe's fireworks, only far more powerful and mysterious. These fleeting yet colossal explosions release more energy in a matter of seconds than our sun will emit in its entire lifetime. But what exactly causes these bursts, and why do they captivate astronomers so deeply? The origins of gamma-ray bursts are thought to stem from two cataclysmic events: the collapse of massive stars into black holes or the violent collision of neutron stars. These events are so energetic that they send shock waves of gamma rays across the cosmos, detectable even from billions of light years away. What makes gamma-ray bursts even more fascinating is their potential to act as cosmic time capsules. Because they originate from such vast distances, they carry clues about the early universe, offering a glimpse into a time when the first stars and galaxies were just beginning to form. By studying these bursts, scientists can piece together the conditions of the universe in its infancy, answering questions about how it evolved into what we see today. But the mystery remains: what exactly triggers these explosions, and why do they vary so dramatically in intensity? As we ponder the forces behind gamma-ray bursts, another cosmic enigma beckons: the Great Attractor. This mysterious gravitational anomaly pulls entire galaxies, including our own Milky Way, toward it at astonishing speeds. What lies at the heart of this cosmic tug of war, and how does it shape the structure of the universe? The answers may lie hidden in the vast reaches of space, waiting to be uncovered. Deep within the vast expanse of the cosmos, there's a force so powerful it's pulling entire galaxies, including our own Milky Way, toward it. This mysterious phenomenon is known as the Great Attractor, a gravitational anomaly that has captivated astronomers for decades. Hidden behind the dense veil of dust and stars in our galactic plane, it remains one of the most elusive enigmas in the universe. But what exactly is it, and why does it wield such an immense gravitational pull? the Great Attractor lies approximately 250 million light-years away in the direction of the constellations Centaurus and Hydra. Despite its colossal influence, studying it is no easy task. The Milky Way's own dust and gas obscure our view, making it like trying to peer through a dense fog. Yet, through advanced technologies like X-ray and infrared telescopes, scientists have begun to piece together clues about this cosmic giant. What they've found suggests it could be a massive cluster of galaxies, each contributing to the gravitational tug we feel. Some theories even propose that dark matter plays a key role, amplifying its pull on everything around it, but the mystery doesn't end there. At the heart of the Great Attractor lies an even deeper question. What could be generating such an extraordinary gravitational force? Is it a supercluster of galaxies, or could it be something even more exotic? Some speculate that it might be a convergence point in the cosmic web, the intricate network of filaments that connects galaxies across the universe. If so, the Great Attractor might not just be pulling us, it could be a vital node in the larger structure of the cosmos. As we ponder the nature of this gravitational powerhouse, it's impossible not to wonder what else might be hiding in the shadows of the universe. The Great Attractor reminds us that even in a cosmos filled with light, some of its most profound secrets remain shrouded in darkness. And as we turn our gaze outward, we find ourselves drawn not just to the Great Attractor, but to the broader mysteries of the cosmic web that binds the universe together. Imagine the universe as a vast, interconnected network, stretching across billions of light-years in an intricate pattern of light and shadow. This is the cosmic web, a colossal skeleton of dark matter and galaxies that forms the backbone of our universe. But what exactly is this web, and how did it come to be? At its core, the cosmic web is a tapestry of filaments, nodes, and voids woven together by the invisible threads of dark matter. These filaments are like cosmic highways, guiding galaxies into clusters and superclusters, while the voids between them remain eerily empty. Scientists believe this structure began to take shape just after the Big Bang, when tiny fluctuations in the density of matter created the seeds for future growth. Over billions of years, gravity pulled these denser regions together, forming the web-like pattern we observe today. But here's the mystery: dark matter, the unseen force that makes up the majority of the universe's mass, played a crucial role in shaping this structure. Without it, galaxies wouldn't have had the gravitational scaffolding needed to form. Yet, despite its importance, dark matter remains one of the greatest enigmas in science. What is it made of? How does it interact with the universe around it? And could the cosmic web hold the key to understanding its true nature? The cosmic web isn't just a relic of the past, it's a living blueprint of the universe's evolution. By studying its filaments and nodes, astronomers can trace the history of galaxy formation and uncover the forces that have shaped the cosmos over billions of years. But could this web also reveal something even more profound? Could it show us the ultimate design of the universe itself? Some scientists speculate that the cosmic web might hold clues to the fundamental laws of physics, offering insights into the nature of space, time, and even the multiverse. As we unravel the mysteries of the cosmic web, another puzzle looms on the horizon: the Hubble tension. This is a discrepancy in the rate at which the universe is expanding, a disagreement between measurements taken locally and those observed in the distant cosmos. What does this tension tell us about the universe's structure, and could it be connected to the cosmic web? Stay tuned as we explore this next cosmic conundrum. One of the most perplexing puzzles in modern cosmology is the Hubble tension, a discrepancy that's shaking the foundations of how we understand the universe. At the heart of this mystery lies a simple question: how fast is the universe expanding? You'd think we'd have a clear answer by now, but the reality is far more complicated. When scientists measure the expansion rate, known as the Hubble constant, using different methods, they get conflicting results. One approach, based on observations of the cosmic microwave background, the faint afterglow of the Big Bang, suggests a slower expansion rate. Meanwhile, measurements using nearby stars and supernova point to a faster rate. These conflicting numbers aren't just a minor inconsistency. They could indicate that something fundamental in our understanding of the cosmos is missing. This discrepancy has sparked a crisis in cosmology. Could it be that our current models of the universe are incomplete? Some scientists propose that new physics might be needed to explain the tension, perhaps an unknown form of dark energy, or even modifications to Einstein's theory of gravity. Others suggest that systematic errors in measurements might be to blame, though repeated experiments and refined techniques haven't resolved the issue yet. The Hubble tension isn't just a technical problem, it's a doorway to potentially groundbreaking discoveries. If resolved, it could lead to a revolution in how we think about the universe's origins and evolution. But what does this mean for the early universe? The Hubble tension hints that our understanding of cosmic inflation, the rapid expansion of the universe moments after the Big Bang, might need revisiting. Could the seeds of this tension lie in the first fractions of a second after the universe began? As we explore the nature of the early universe's inflation, we might find clues that help unravel this cosmic mystery. After all, the universe has a way of surprising us, and the Hubble tension is just one of its many enigmatic whispers. Picture this, a universe so tiny it could fit in the palm of your hand, suddenly stretching out in every direction faster than the speed of light. This isn't science fiction, it's cosmic inflation, one of the most mind-bending ideas in modern cosmology. But what exactly caused this explosive expansion, and how did it shape the universe we see today? Let's unpack this extraordinary event that happened just a fraction of a second after the Big Bang. Cosmic inflation is the theory that the universe underwent a rapid, exponential expansion during its earliest moments. Think of it like blowing up a balloon at an unimaginable speed, except instead of rubber, it's the fabric of space itself stretching. This theory solves some of the biggest puzzles in cosmology, like why the universe looks so uniform in every direction. If you've ever looked at the cosmic microwave background, the afterglow of the Big Bang, you'll notice it's remarkably smooth. That uniformity is one of the strongest pieces of evidence for inflation. Without it, we'd expect to see far more variation in the temperature and density of the early universe. But here's where things get truly fascinating. What actually triggered this rapid expansion? Scientists believe it had something to do with a mysterious field of energy called the inflaton field. Imagine this field as a kind of cosmic switch. Once it flipped, it sent space into overdrive, pushing everything apart at an incredible rate. And just as suddenly as it began, inflation stopped, leaving the universe to continue expanding at a slower pace, which it still does today. But why did it stop? That's another mystery. Some suggest it was like a bubble popping, releasing energy that set the stage for the formation of particles, galaxies, and eventually us. Now, here's a thought that might blow your mind. Could cosmic inflation happen again? Some theories propose that inflation isn't a one-time event but a recurring phenomenon, with pockets of the universe eternally expanding while others remain stable. It's a staggering idea, suggesting that our universe might just be one bubble in an endless cosmic foam. This leads us to another intriguing question. What shape did all this expansion give the universe? Is it flat, curved, or something even stranger? The answer could redefine our understanding of reality itself. When we look up at the night sky, it's easy to imagine the universe as an endless expanse stretching in every direction. But what if the cosmos isn't infinite? What if it has a shape, a geometry that defines its structure and ultimately its fate? This is one of the most profound questions in cosmology. Is the universe flat, closed like a sphere, or open like a saddle? The answer lies in the fabric of spacetime itself. According to Einstein's theory of general relativity, the universe's geometry is determined by the amount of matter and energy it contains. If the density of the universe matches a specific critical value, space is flat, meaning parallel lines remain parallel forever, and the rules of Euclidean geometry hold true. But if the universe contains more matter and energy than this critical density, it curves back on itself, forming a closed, spherical shape. In this scenario, if you could travel far enough in one direction, you'd eventually end up where you started, like circumnavigating the globe. On the other hand, if the universe has less matter and energy than the critical density, it would curve outward, creating an open, saddle-like shape where parallel lines diverge over time. So, how do we know which of these possibilities is true? The cosmic microwave background, or CMB, holds the key. This faint glow of radiation left over from the Big Bang is like a cosmic fingerprint revealing the universe's early conditions. Tiny temperature fluctuations in the CMB provide clues about the universe's geometry. Measurements from missions like the Planck satellite suggest that the universe is remarkably close to being flat, with only the tiniest deviations. But close to flat doesn't mean perfectly flat. It leaves room for debate and further exploration. What's even more fascinating is how dark energy plays into this cosmic puzzle. This mysterious force driving the accelerated expansion of the universe seems to dominate its energy content. If dark energy continues to push the universe apart, a flat or open universe would expand forever, growing colder and darker as galaxies drift apart. A closed universe, however, might one day stop expanding and collapse back in on itself in a big crunch. The shape of the universe isn't just a matter of geometry, it's a window into its origins and destiny. A flat universe suggests a delicate balance in the early moments of the Big Bang, while a closed or open universe hints at a different cosmic recipe. Each possibility raises new questions. Was the universe always destined to take this shape, or did random fluctuations during its infancy set it on this path? As we ponder the universe's shape, another question arises. How old is it really? The answer might surprise you, and it's where our journey takes us next. The universe, our vast cosmic home, has been around for a long, long time. But just how old is it? Scientists have been working tirelessly to pin down this number, and while we've made incredible strides, the answer isn't as straightforward as you might think. Let's dive into how we estimate the age of the universe and why this question is so fascinating and, at times, so puzzling. One of the key tools in this cosmic detective work is the Hubble constant. Named after the legendary astronomer Edwin Hubble, this number measures how fast the universe is expanding. By tracking the speed at which galaxies are moving away from us, scientists can essentially rewind the cosmic tape to estimate when everything began, the Big Bang. Current calculations suggest the universe is around 13.8 billion years old. But here's the catch: measuring the Hubble constant isn't as simple as it sounds. Different methods, like observing distant supernova or studying the cosmic microwave background, the faint afterglow of the Big Bang, sometimes give slightly different results. These discrepancies leave room for uncertainty, and they've sparked intense debates among astronomers. Speaking of the cosmic microwave background, or CMB, it's another critical piece of the puzzle. This faint radiation, detectable across the entire sky, is like a snapshot of the universe when it was just 380,000 years old. By analyzing tiny fluctuations in the CMB, scientists can infer the universe's age with remarkable precision. Yet even here, questions linger. Could there be something we're missing in this ancient light? Could our understanding of the cosmos be fundamentally flawed? What if the universe is older or younger than we think? An older universe might mean we've underestimated the rate of expansion or overlooked some hidden factor influencing cosmic growth. A younger universe, on the other hand, could challenge our entire framework of physics. It's a humbling reminder that, despite all we've learned, the cosmos still holds secrets we've yet to uncover. So, could our understanding of the universe's age be wrong? It's possible, and that's what makes this question so thrilling. As we grapple with these uncertainties, we're not just uncovering the past, we're shaping the future of cosmology. But this isn't the only mystery that keeps scientists up at night. What about the universe's size? Is it infinite, or does it have an end? Buckle up, because that's where we're headed next. Have you ever tried to wrap your mind around the sheer size of the universe? It's one of those questions that feels almost impossible to answer, yet scientists have been grappling with it for centuries. The truth is, we don't know for sure whether the universe is infinite or finite. What we do know is that the observable universe, the part we can see and measure, stretches an astonishing 93 billion light-years across. That's the distance light has traveled since the Big Bang, some 13.8 billion years ago. But here's the kicker, that's just the part we can observe. Beyond that, it's a mystery. What lies beyond the observable universe is one of the most tantalizing questions in cosmology. Some theories suggest that the universe could be infinite, stretching endlessly in all directions. Others propose it might be finite but unbounded, like the surface of a sphere. If you traveled far enough in one direction, you might eventually loop back to where you started. Then there's the mind-bending idea of a multiverse, where our universe is just one of countless others, each with its own unique set of physical laws. Could the universe be far larger or even smaller than we imagine? The answer might depend on its topology, the shape and structure of space-time itself. This brings us to another fascinating puzzle, the composition of the universe. What is it made of, and how does that shape its ultimate size and fate? From dark energy driving its expansion to dark matter holding galaxies together, the universe is far more complex than meets the eye. And as we explore these mysteries, we're left with even more questions about the nature of reality itself. Could the universe be infinite, or is it just a tiny corner of something much, much bigger? The search for answers continues, and every discovery brings us closer to understanding the true scale of the cosmos. When we look up at the night sky, it's easy to feel like we're surrounded by an endless expanse of stars, planets, and galaxies. But what exactly is the universe made of? The answer might surprise you, because the stuff we can see and touch, the so-called ordinary matter that makes up everything from stars to smartphones, accounts for just 5% of the universe's total composition. The rest, it's a cosmic cocktail of dark matter and dark energy, two mysterious forces that shape the cosmos in ways we're only beginning to understand. Let's break it down. Ordinary matter, the atoms and molecules we're familiar with, is the building block of planets, stars, and even life itself. Yet, it's the smallest slice of the cosmic pie. Dark matter, which makes up about 27% of the universe, doesn't emit light or energy, making it invisible to our telescopes. We only know it exists because of its gravitational effects. It holds galaxies together and bends light in ways that ordinary matter alone can't explain. Then there's dark energy, the most enigmatic of all, accounting for a staggering 68% of the universe. This force is driving the accelerated expansion of the cosmos, pushing galaxies apart faster than gravity can pull them together. So why is ordinary matter so rare? The answer lies in the early moments of the universe. During the Big Bang, matter and antimatter were created in nearly equal amounts, but something tipped the scales in favor of matter, leaving us with the atoms that form everything around us. The rest of the universe, it seems, is dominated by forces and particles that defy our current understanding of physics. This raises a tantalizing question. Could there be other components of the universe we haven't even detected yet? Perhaps hidden dimensions, exotic particles, or entirely new forms of energy are waiting to be discovered, reshaping our understanding of reality itself. As we ponder these mysteries, we're led to another question. What about the fundamental constants of the universe? Why do they have the precise values they do, and what happens if they change? These constants, like the speed of light or the strength of gravity, aren't just arbitrary numbers. They're the fine-tuned parameters that make life and the universe as we know it possible. But what if they're not constant at all? What if they fluctuate or vary across different parts of the cosmos? This idea challenges everything we think we know about the laws of physics, and it's a question that brings us to the edge of our understanding and perhaps to the next great discovery. Have you ever stopped to wonder if the very rules that govern our universe might not be as fixed as we think? Take the speed of light, for example. Its value is etched into the fabric of physics as a constant, an unchanging number that underpins so much of what we understand about space, time, and energy. But what if it isn't as constant as we believe? What if, over vast stretches of time or across unimaginable distances, the speed of light, or even the gravitational constant, could shift ever so slightly? It's a question that challenges the very foundation of our understanding of reality. These constants, like the fine structure constant or Planck's constant, are the building blocks of the universe. They're the numbers we plug into equations to predict how stars burn, how planets orbit, and even how atoms bind together. For centuries, we've assumed they're immutable, unyielding truths. But what if they're not? Some scientists have begun to ask whether these constants could vary over time or space, subtly altering the laws of physics in ways we've yet to detect. Imagine a universe where, billions of years ago, light traveled just a fraction faster or gravity was a little stronger. How would that change the cosmos as we know it? Experiments are already underway to test these ideas. By studying distant quasars and ancient light from the early universe, researchers can compare the behavior of these constants today with how they might have behaved billions of years ago. So far, the evidence suggests they've remained remarkably stable, but even the tiniest hint of variation could open up entirely new realms of physics. It's like discovering that the rules of chess can change mid-game, forcing us to rethink everything we thought we knew about the game itself. And then there's the symmetry of the universe. If constants aren't as constant as we thought, what does that mean for the elegant symmetries we see in nature, like the way particles and antiparticles mirror each other, or the way forces balance out across the cosmos? Symmetry has long been a guiding principle in physics, helping us uncover hidden patterns and predict new phenomena. But if the constants that define those symmetries can shift, could the universe itself be rewriting its own rulebook as it evolves? It's a profound question that takes us to the very heart of what it means to understand the cosmos. And as we explore this idea, it leads us to an even more fundamental mystery. What is the true nature of the universe's symmetry, and how does it shape everything we see? Have you ever wondered why the universe seems so perfectly balanced, as if it were designed with an artist's precision? This is where the concept of symmetry steps in, a principle so deeply woven into the fabric of reality that it governs everything from the tiniest particles to the vast cosmic structures we see today. Symmetry isn't just about beauty or balance, it's a cornerstone of the laws of physics. Think about it, the equations that describe the forces of nature, like gravity or electromagnetism, are symmetrical. They work the same way whether you're looking forward or backward in time, or even if you're flipping the entire system like a mirror image. This isn't just a coincidence, it's a clue to something far more profound. But here's where things get even more intriguing. While symmetry seems to be the universe's default setting, it's not always perfect. In fact, broken symmetry plays a crucial role in shaping the cosmos. Take the early universe, for example. In its first moments, everything was perfectly symmetrical, a hot, dense soup of energy where forces and particles were indistinguishable. But as the universe expanded and cooled, that symmetry broke, like a spinning top wobbling and settling into a new state. This breaking of symmetry is what allowed particles to gain mass, stars to form, and galaxies to take shape. Without it, the universe as we know it wouldn't exist. So why is symmetry so prevalent? Is it a fundamental property of the universe, or are we simply seeing patterns because of how we observe it? Some scientists argue that symmetry is built into the very laws of physics, a kind of cosmic blueprint that dictates how reality operates. Others suggest that what we perceive as symmetry might just be a byproduct of our limited perspective, a way for our brains to make sense of the chaos. Either way, the prevalence of symmetry raises a fascinating question. Is the universe inherently balanced, or is balance something we impose on it through our understanding? And as we ponder this, another mystery emerges, one that ties symmetry to the very nature of the universe's entropy. Entropy, often described as the measure of disorder, seems to be the opposite of symmetry's order and balance. Yet, these two concepts are deeply connected. As the universe evolves, its entropy increases, driving systems toward chaos. But even in this chaos, pockets of symmetry persist, like the spiral arms of galaxies or the crystalline structures of minerals. Could entropy and symmetry be two sides of the same cosmic coin, each shaping the universe in its own way? This interplay between order and disorder, symmetry and entropy, hints at a deeper truth about the universe, one that we're only beginning to unravel. And as we explore these concepts, we're reminded that the cosmos is full of mysteries waiting to be discovered, each one more captivating than the last. Have you ever wondered why things seem to fall apart over time? Why does a hot cup of coffee cool down, or why does a tidy room eventually become messy? The answer lies in a fascinating concept called entropy, a fundamental principle of the universe that governs the direction of change. Entropy is often described as the measure of disorder in a system, and it's at the heart of the second law of thermodynamics. This law states that in any isolated system, entropy always increases over time. In other words, the universe has a natural tendency to move from order to disorder. But why is this the case, and what does it mean for the cosmos as a whole? When we look at the universe today, we see a vast expanse filled with galaxies, stars, and planets, all seemingly ordered structures. Yet, the second law of thermodynamics tells us that this order is fleeting. Over billions of years, stars will burn out, galaxies will drift apart, and the universe will continue to expand and cool. Eventually, it may reach a state of maximum entropy, often referred to as the heat death of the universe, where energy is evenly distributed and no more work can be done. It's a cosmic fate that feels both inevitable and profoundly mysterious. What's even more puzzling is the question of why the early universe had such low entropy. Imagine the Big Bang, a moment of incredible energy and density, yet also one of extraordinary order. How did the universe start in such a highly ordered state, only to evolve toward greater disorder over time? This mystery is deeply connected to the concept of time's arrow, the idea that time moves in one direction from the past to the future. Some scientists suggest that entropy is the key to understanding why we perceive time as flowing forward. Without entropy, the distinction between past and future might not exist. This leads us to another intriguing question. Could entropy hold clues about the fundamental nature of the universe's information? If entropy is a measure of disorder, it's also closely tied to the amount of information in a system. the more disordered a system becomes, the more information is required to describe it. This connection between entropy and information has sparked groundbreaking theories, including the idea that the universe might be a kind of cosmic computer, processing information as it evolves. It's a concept that blurs the lines between physics and philosophy, inviting us to rethink our understanding of reality itself. As we ponder the role of entropy in shaping the universe, we're reminded that even chaos has its own kind of order. The universe's journey from low entropy to high entropy is not just a story of decay. It's the very process that makes life, stars, and galaxies possible. Without entropy, the cosmos would be static and unchanging, a frozen snapshot without the dynamic beauty we see today. So, while entropy may lead us toward an uncertain future, it's also the force that breathes life into the universe, shaping its past, present, and ultimate destiny. But what happens to information when it's swallowed by a black hole? This is where things get truly mind-bending. According to Einstein's theory of general relativity, once something crosses a black hole's event horizon, it's gone forever, lost to the universe. But quantum mechanics tells a different story. In the quantum world, information can never be destroyed. It's a fundamental rule. So when these two ideas collide, we're left with the black hole information paradox, a cosmic tug of war between two of physics' most important theories. If information truly can't be destroyed, where does it go when it enters a black hole? Some scientists suggest that black holes might not be the cosmic vacuum cleaners we once thought. Instead, they could be storing information in ways we don't yet understand. One fascinating idea is the holographic principle, which proposes that all the information about what falls into a black hole could be encoded on its surface like a cosmic DVD. Imagine the entire three-dimensional contents of a black hole compressed onto a two-dimensional boundary. It sounds like science fiction, but it's a serious theory that could reconcile the clash between quantum mechanics and relativity. This leads us to an even bigger question. Could the universe itself be a vast information processor? Think about it. Every particle, every interaction, every event, what if it's all just data being processed on a cosmic scale? Some physicists have started to explore this idea, suggesting that the universe might operate like a quantum computer, with information as its fundamental currency. It's a radical thought, but one that could reshape how we understand reality itself. And speaking of reality, let's shift gears to another profound mystery, the fine-tuning of the universe. Why do the laws of physics seem so perfectly calibrated to allow for stars, planets, and life? It's as if the universe were designed with us in mind, or is it just a cosmic coincidence? This fine-tuning is one of the most intriguing puzzles in science, and it raises questions that might just take us to the edge of our understanding. Have you ever stopped to wonder why the universe seems so perfectly suited for life? The laws of physics, the fundamental constants like gravity and the strength of electromagnetism, are precisely calibrated to allow stars to form, planets to orbit, and life to emerge. If any of these values were even slightly different, the universe as we know it wouldn't exist. This remarkable precision has led scientists to propose the idea of fine-tuning, a concept that raises profound questions about the nature of reality. At the heart of this discussion is the anthropic principle, which suggests that the universe must be compatible with the conscious life that observes it. In other words, if the universe weren't fine-tuned, we wouldn't be here to question it. But this leads to a deeper mystery. Is this fine-tuning the result of intentional design, or is it simply a cosmic coincidence? Some argue that the universe's constants point to a creator, while others propose that we're just one of countless universes in a vast multiverse, each with its own set of physical laws. The multiverse theory offers a fascinating explanation for fine-tuning. If an infinite number of universes exist, each with different constants and laws, it's statistically inevitable that at least one would have the conditions necessary for life to arise. In this scenario, our universe isn't special, it's just the one where everything aligned in our favor. But this raises even more questions. How could we ever test the existence of other universes? And if the multiverse is real, what does that mean for our understanding of reality? These ideas challenge us to think beyond our own universe and consider the possibility that ours is just one piece of a much larger cosmic puzzle. Whether fine-tuning is evidence of design or a stroke of luck, it forces us to confront the extraordinary balance that makes our existence possible. As we delve deeper into the mysteries of the cosmos, the nature of the multiverse remains one of the most tantalizing frontiers in modern science. But what if our universe isn't the only one? What if, beyond the edges of our observable cosmos, there are countless other universes, each with its own unique set of physical laws, its own stars, planets, and perhaps even life? This is the fascinating idea behind the multiverse, a concept that challenges everything we think we know about reality. Imagine a cosmic tapestry where every thread is a separate universe, each one governed by different rules. Some might have stronger gravity, others might have no gravity at all. Some could be filled with light, while others might exist in perpetual darkness. The possibilities are as endless as the universes themselves. Theories like eternal inflation suggest that our universe is just one bubble in a vast cosmic foam, constantly expanding and spawning new universes. Meanwhile, string theory introduces the idea of a landscape of possible universes, each one corresponding to a different configuration of the fundamental forces and particles. These ideas aren't just science fiction, they're serious scientific hypotheses that attempt to explain why our universe has the properties it does. If the multiverse exists, it could mean that our universe is just one of many, each one a variation in an infinite cosmic experiment. But here's the big question: could we ever find evidence of these other universes? Some scientists think we might. Tiny imprints in the cosmic microwave background, the afterglow of the Big Bang, could hold clues. Others suggest that collisions between our universe and another might leave behind detectable marks. However, the challenge is immense. If these universes exist beyond our own, they might be forever out of reach, separated by distances and laws of physics we can't even comprehend. This leads us to another mind-bending idea, the holographic principle. What if our universe, with all its vast complexity, is actually a projection of information stored on a two-dimensional surface? It sounds like something out of a sci-fi movie, but it's a serious proposal that attempts to reconcile quantum mechanics and gravity. The holographic principle suggests that everything we see, stars, galaxies, even ourselves, might be nothing more than a cosmic hologram, a kind of illusion created by the way information is encoded on the boundary of our universe. Could this be the key to understanding the true nature of reality? Or is it just another layer of the cosmic mystery that keeps us guessing? What if everything we see, touch, and experience, the vastness of galaxies, the shimmering light of stars, even the tiniest particles, isn't quite as real as we think? Enter the holographic principle, one of the most mind-bending ideas in modern physics. It suggests that our three-dimensional universe might actually be a projection of information encoded on a two-dimensional surface, like a cosmic hologram. Imagine the universe as a movie screen, where every star, planet, and black hole is just a detailed image projected from a flat surface. Sounds like science fiction, right? But this idea isn't pulled from thin air. It's rooted in some of the most puzzling mysteries of physics, particularly black holes and quantum gravity. Black holes, those enigmatic regions where gravity is so intense that not even light can escape, play a starring role in this theory. When matter falls into a black hole, what happens to all that information? According to the holographic principle, the information isn't lost, it's somehow encoded on the black hole's event horizon, the boundary surrounding it. This idea ties into quantum gravity, the quest to unify Einstein's theory of general relativity with quantum mechanics. If the universe truly operates like a hologram, it could mean that everything we perceive, space, time, and matter, is just a surface-level representation of deeper, more fundamental information. The implications are staggering. If the universe is simpler than we think, if it's essentially a two-dimensional code, it could revolutionize our understanding of reality. It might even provide a way to reconcile the weirdness of quantum mechanics with the elegance of general relativity, two frameworks that have stubbornly resisted unification. But here's the kicker: if the universe is a hologram, what's generating the projection, and what lies beyond the screen? These questions push the boundaries of our imagination and challenge us to rethink the very fabric of existence. And speaking of fabric, this leads us to another fascinating mystery, the quantum foam. If the universe operates on a holographic principle, then the tiny, frothy fluctuations at the smallest scales of space and time, what physicists call quantum foam, might hold the key to understanding how this cosmic hologram works. Is the foam the pixels of the universe, the building blocks of the hologram? Or is it something even stranger, hinting at a deeper layer of reality we've yet to uncover? The answers might lie in the strange, unpredictable behavior of particles at the quantum level, where the rules of classical physics break down and the universe reveals its most enigmatic secrets. What if the smooth, continuous fabric of spacetime we imagine is actually a chaotic, frothy sea at the tiniest scales? This is the mind-bending idea behind quantum foam, a concept that suggests spacetime isn't as serene as it seems. At scales so small they're measured in Planck lengths, which are a billionth of a trillionth of a trillionth of a meter, spacetime might be a turbulent, bubbling froth. Picture it like the surface of a boiling pot, but instead of water, it's the very structure of reality itself. This quantum foam could be the playground where the rules of quantum mechanics and gravity collide, offering clues to a theory of everything. But here's the catch: quantum foam isn't just a wild idea. It's a prediction of quantum gravity, a framework that aims to unify Einstein's general relativity with the bizarre world of quantum mechanics. If spacetime is foamy, it could explain why gravity behaves so differently from the other fundamental forces. Yet, observing this foam is a monumental challenge. It's so tiny and so fleeting that even our most advanced instruments can't detect it directly. Some scientists suggest that high-energy particles traveling across the universe might carry subtle imprints of this foam, but so far the evidence remains elusive. So, could quantum foam be the missing link in physics? It's a tantalizing possibility. If proven, it might not only bridge the gap between quantum mechanics and gravity, but also reshape our understanding of reality itself. After all, if spacetime is foamy at its core, what does that say about the universe's fundamental nature? And speaking of fundamental mysteries, this leads us to another profound question. What about the universe's vacuum energy? Why does empty space seem to hold energy, and what role does it play in the cosmos? The answers might lie in the very fabric of spacetime itself. Imagine a vast, empty space, a void so complete that not even light or matter exists within it. You might think this emptiness holds no energy, but the universe has a surprise for us. Even in the deepest vacuum, energy lingers, woven into the fabric of space itself. This is vacuum energy, a concept that has left scientists scratching their heads for decades. According to quantum field theory, the vacuum should be teeming with energy, so much so that it should have profound effects on the cosmos. Yet, when we measure it, the energy is astonishingly low, so low that it defies our best predictions. This puzzling gap between theory and observation is known as the cosmological constant problem, and it's one of the most profound mysteries in modern physics. The cosmological constant, a term introduced by Einstein, was originally meant to describe a static universe. Today, it's closely tied to dark energy, the mysterious force driving the accelerated expansion of the universe. But here's the catch: the amount of vacuum energy predicted by quantum mechanics is a staggering 120 orders of magnitude larger than what we observe. That's a 1 followed by 120 zeros, a number so vast it's almost impossible to comprehend. Why is the universe's vacuum energy so much lower than it should be? This question isn't just a mathematical curiosity, it's a window into the very nature of reality. Some theories suggest that unknown physics might be at play, cancelling out the excess energy in ways we don't yet understand. Others propose that multiple universes exist, each with different values of vacuum energy, and we just happen to live in one where the energy is unusually low. Then there's the possibility that our understanding of quantum field theory is incomplete, missing a crucial piece of the puzzle. Each of these ideas offers a tantalizing glimpse into what might lie beyond our current knowledge, but none have provided a definitive answer. So, could vacuum energy hold the key to understanding the universe's expansion? It's a question that keeps physicists awake at night. If we can solve this mystery, it might reveal not only the true nature of dark energy, but also the fundamental laws governing space and time. And as we ponder this cosmic riddle, it's worth noting that the universe's quantum fabric might hold even more surprises. For instance, the strange phenomenon of quantum entanglement, where particles remain connected across vast distances, could be deeply intertwined with the nature of vacuum energy. What secrets might this connection reveal about the cosmos? The journey to uncover these answers is just beginning, and every discovery brings us closer to understanding the universe's deepest mysteries. What if I told you that two particles could be so deeply connected that changing one instantly affects the other, no matter how far apart they are, even if that distance spans the entire universe? This isn't science fiction, it's quantum entanglement, a phenomenon so strange that even Albert Einstein famously called it spooky action at a distance. At the heart of quantum mechanics, entanglement challenges everything we thought we knew about how the universe works. Imagine two particles born together in the same event, becoming intertwined in such a way that their properties are linked. If you measure one and find it spinning clockwise, the other will instantly spin counterclockwise, even if it's light years away. This connection happens faster than the speed of light, defying the rules of classical physics. But how does this work? Experiments like the Bell test have proven that entanglement is real, showing that particles don't just seem connected, they are connected in a way that transcends space and time. This raises profound questions about the nature of reality itself. Could the universe be far more interconnected than we ever imagined? And if particles can communicate instantaneously, could entanglement be the key to faster-than-light communication? While it's tempting to think so, scientists are quick to point out that entanglement doesn't allow us to send messages faster than light. The connection is mysterious and instantaneous, but it doesn't carry information in the way we'd need for communication. Still, the possibilities it opens for quantum computing and secure communication are nothing short of revolutionary. So, what's really going on here? Is entanglement revealing a hidden layer of reality where distance and separation are illusions? Or is it hinting at something even stranger, like the idea that the universe is fundamentally non-local, with everything connected in ways we're only beginning to understand? As we peel back the layers of this quantum mystery, we're left with even more questions than answers. And speaking of mysteries, what if I told you that particles can do something even more bizarre than entanglement? What if they could pass through barriers as if they weren't even there? That's where quantum tunneling comes into play, a phenomenon that makes the impossible seem almost routine. But that's a story for our next cosmic question. What if I told you that particles can do the impossible, passing straight through barriers that should stop them in their tracks? This isn't science fiction, it's a real phenomenon called quantum tunneling, and it's one of the strangest and most fascinating quirks of the quantum world. At the subatomic level, particles don't always play by the rules we're used to. Instead of bouncing off an obstacle, they can sometimes appear on the other side as if they've teleported through it. It's like throwing a ball at a wall and watching it magically appear on the other side without breaking the wall or the ball. So, how does this happen? Quantum tunneling occurs because particles in their quantum state don't behave like solid objects. Instead, they're more like waves of probability. When a particle encounters a barrier, there's a tiny but real chance it can tunnel through it thanks to the uncertainty principle. This principle tells us that we can never know a particle's exact position and momentum at the same time. Because of this uncertainty, particles have a kind of built-in flexibility, allowing them to slip through barriers that would be impossible to cross in the classical world. This phenomenon isn't just a curious oddity, it's essential to some of the most important processes in the universe. Take nuclear fusion, for example. Inside stars, hydrogen nuclei fuse together to form helium, releasing the energy that powers the cosmos. But for this to happen, the nuclei have to overcome a powerful force of repulsion. Without quantum tunneling, they wouldn't be able to get close enough to fuse, and stars, including our sun, wouldn't shine. It's a cosmic cheat code that keeps the universe alive. Quantum tunneling also plays a starring role in the future of technology. In quantum computing, particles tunnel through energy barriers to perform calculations that would take classical computers centuries to solve. This ability could revolutionize fields like cryptography, materials science, and artificial intelligence. But here's the kicker: even though we use quantum tunneling, we still don't fully understand how it works. It's a reminder that the quantum world operates on rules that defy our everyday intuition. Which brings us to the bigger question: could quantum tunneling hold the key to understanding the nature of reality itself? Some scientists think it might. If particles can exist in multiple places at once and pass through barriers, what does that say about the fabric of the universe? Is reality fundamentally uncertain, as quantum mechanics suggests? Or is there a deeper layer of order beneath the chaos that we're only beginning to glimpse? These questions take us into the realm of quantum decoherence, where the weirdness of the quantum world meets the stability of the universe we experience. And that's where the story gets even more intriguing. Here's the next part of the script following your outline segment. Imagine if every object around you, your coffee cup, your chair, even the ground beneath your feet, was constantly flickering between multiple states, existing in countless possibilities all at once. Sounds like science fiction, right? Yet this is precisely how particles behave in the quantum world. So why don't we see these bizarre effects in our everyday lives? The answer lies in a fascinating phenomenon known as quantum decoherence. Quantum decoherence is the process by which quantum systems lose their strange, wave-like behavior and start to act more like the predictable, solid objects we're familiar with. At the quantum level, particles exist in a superposition of states, meaning they can be in multiple places or states simultaneously. But as these particles interact with their environment, whether it's air molecules, light, or even other particles, they become entangled with countless other particles. This entanglement causes the delicate quantum states to collapse into a single, definite state. This process helps explain why we don't see quantum effects in the macroscopic world. It's not that quantum mechanics stops working at larger scales. It's just that the environment around us is constantly measuring and interacting with everything, leading to decoherence. But here's where things get even more intriguing. Decoherence doesn't necessarily solve the measurement problem. The mystery of how and why quantum systems transition from multiple possibilities to a single observed outcome. It merely shifts the question, what exactly counts as a measurement, and how does the universe decide when to collapse these probabilities? The implications of decoherence go far beyond just explaining why we don't see quantum weirdness in our daily lives. It challenges our understanding of reality itself. If quantum mechanics governs everything, how does the classical world, the world of definite positions, clear boundaries, and predictable outcomes emerge from such a fuzzy, probabilistic foundation? Some scientists believe decoherence could be the missing link between the quantum and classical realms, a bridge that helps us understand how the universe transitions from the bizarre to the familiar. But the mystery doesn't end there. Decoherence also raises profound questions about the nature of quantum gravity. If gravity is a fundamental force, how does it fit into this quantum framework? Could understanding decoherence help us uncover the secrets of quantum gravity, the elusive theory that would unify Einstein's general relativity with quantum mechanics? As we peel back the layers of quantum decoherence, we're left with even more questions than answers. How does the universe decide which quantum states to collapse into? Is there a deeper reality hidden beneath the surface of our observations? And what role does quantum gravity play in shaping the cosmos? These are the mysteries that keep physicists awake at night, and they might just hold the key to unlocking the true nature of our universe. Imagine a universe where the rules of gravity, as we know them, don't quite fit. Where the colossal forces that shape galaxies and the tiny, unpredictable behavior of particles exist in separate worlds, refusing to play by the same rules. This is the puzzle of quantum gravity, the missing link in physics that could unite the two most powerful theories of our time, Einstein's general relativity and quantum mechanics. General relativity explains the grand cosmic dance, planets orbiting stars, black holes warping space-time, while quantum mechanics governs the subatomic realm, where particles pop in and out of existence in a blur of uncertainty. But when these two theories collide, they don't harmonize. They clash, leaving scientists with a gaping hole in our understanding of how the universe truly works. So, how do we bridge this divide? One promising path is string theory, which imagines the fundamental building blocks of the universe not as point-like particles, but as tiny, vibrating strings. These strings, dancing in higher dimensions, could potentially explain everything from gravity to the forces that bind atoms together. It's an elegant idea, but one that comes with a catch. String theory operates on scales so unimaginably small that testing it directly is, for now, beyond our reach. Then there's loop quantum gravity, another contender in this cosmic quest. This theory suggests that space-time itself is woven from tiny, discrete loops, creating a sort of quantum fabric. It's a radically different approach, but like string theory, it faces the same hurdle. How do we prove it? The challenge of testing these theories is monumental. We're talking about phenomena that occur at the Planck scale, far smaller than anything we can observe with current technology. Even the most advanced particle accelerators, like the Large Hadron Collider, can't reach the energies needed to probe these realms. And without experimental evidence, these ideas remain in the realm of mathematical elegance rather than proven fact. Yet, the pursuit of quantum gravity isn't just an academic exercise. It's a journey to answer some of the most profound questions about our universe. Could it explain the singularity at the heart of black holes, or reveal the true nature of the Big Bang? And perhaps most tantalizingly, could it unlock the secrets of dark energy and dark matter, the invisible forces that make up most of the cosmos. As we edge closer to understanding quantum gravity, we're also drawn deeper into the mysteries of string theory. What if these tiny, vibrating strings aren't just the key to unifying physics, but also the threads that weave the very fabric of reality? What if the universe itself is a symphony of strings resonating in dimensions beyond our perception? These questions lead us to the next frontier in our exploration, where the nature of the universe itself may be written in the language of strings. What if everything in the universe, every particle, every force, even the fabric of space and time itself, could be explained by something as simple as a vibrating string? This is the bold promise of string theory, a groundbreaking idea that has captivated physicists for decades. At its core, string theory suggests that the fundamental building blocks of reality aren't point-like particles but incredibly tiny, one-dimensional strings. These strings vibrate at different frequencies, much like the strings of a guitar, and it's these vibrations that give rise to everything we see, from the smallest quark to the vast expanse of galaxies. But string theory isn't just about particles. It's often called the theory of everything because it aims to unify all the forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces into a single, elegant framework. Imagine a cosmic symphony where every force and particle is a note played by these vibrating strings. That's the dream string theory is chasing, and if it's correct, it could provide answers to some of the deepest questions in physics, like what happened at the Big Bang or what lies at the heart of black holes. Yet, as beautiful as this theory is, it comes with its own set of challenges. One of the biggest hurdles is that string theory predicts the existence of extra dimensions, up to 10 or even 11 in some versions. These dimensions are thought to be curled up so tightly that we can't detect them, but they're essential for the math to work. Testing these ideas, however, is incredibly difficult. The scales involved are so small and the energies so high that current technology simply can't probe them. This has led some to question whether string theory is truly a scientific theory or more of a mathematical framework. Still, the implications of string theory are mind-bending. If extra dimensions exist, what would they look like? Could they hold the key to understanding dark matter or dark energy? And if string theory is correct, could it really be the ultimate theory of the universe? These are questions that keep physicists up at night, and while we don't have definitive answers yet, the pursuit of these ideas pushes the boundaries of what we know. Now, as we venture deeper into the mysteries of the cosmos, another intriguing idea emerges: loop quantum gravity. Unlike string theory, which imagines tiny strings, this approach suggests that space and time themselves are woven from discrete loops, creating a kind of quantum fabric. Could this be the missing piece in our understanding of the universe's structure? Let's explore this fascinating concept next. What if the fabric of space-time isn't smooth and continuous, but instead made up of tiny, indivisible loops? That's the bold idea behind loop quantum gravity, a fascinating theory that dares to challenge string theory in the quest to unify quantum mechanics and general relativity. While string theory imagines the universe as a symphony of vibrating strings, loop quantum gravity paints a very different picture, one where space-time itself is woven from discrete, quantized threads. It suggests that space isn't infinitely divisible, but instead exists in tiny, finite loops like pixels on a cosmic screen. This theory doesn't just tweak our understanding of the universe, it rewrites it entirely. But how does loop quantum gravity actually work? At its core, it proposes that space-time is quantized, meaning it's broken down into the smallest possible units. These units form a network of loops, creating a structure that's often compared to a fabric or a web. One of the most intriguing predictions of this theory is that space-time has a granular nature, a kind of quantum foam that becomes apparent at the tiniest scales. This granularity could have profound implications for our understanding of black holes, the Big Bang, and even the nature of time itself. For instance, loop quantum gravity suggests that the Big Bang might not have been a singular, explosive event but rather a big bounce, where the universe emerged from a previous collapsing phase. Of course, like any groundbreaking theory, loop quantum gravity faces its share of challenges. One of the biggest hurdles is testing its predictions. Unlike string theory, which has inspired experiments like those at the Large Hadron Collider, loop quantum gravity operates at scales so small that current technology can't directly probe them. This raises the question, can a theory that's so difficult to test ever gain widespread acceptance? Yet, its proponents argue that its mathematical elegance and potential to resolve long-standing paradoxes make it a worthy contender in the search for a unified theory. So, could loop quantum gravity offer a simpler solution than string theory? It's a compelling question. While string theory requires extra dimensions and a vast landscape of possible universes, loop quantum gravity sticks to the 4 dimensions we know, no frills, no extras. It's a minimalist approach that appeals to those who prefer Occam's razor, the idea that the simplest explanation is often the best. But simplicity doesn't always mean correctness, and the debate between these two theories is far from settled. As we ponder these competing visions of the cosmos, another layer of complexity emerges: M-theory. This enigmatic framework attempts to unify the various versions of string theory, suggesting that they're all different facets of a single, overarching theory. Could M-theory hold the key to reconciling loop quantum gravity and string theory? Or is there an even deeper truth waiting to be uncovered? The search for answers continues, reminding us that the universe is far stranger and more wondrous than we've yet imagined. What if there's a theory so powerful, so all-encompassing, that it could tie together every fundamental force in the cosmos? Enter M-theory, often called the mother of all theories. This groundbreaking idea emerged in the 1990s as a way to unite the 5 competing versions of string theory into one cohesive framework. Imagine it as a cosmic puzzle solver, weaving together gravity, electromagnetism, and the forces that bind atoms into a single, elegant tapestry. But here's the kicker. Despite its potential to revolutionize our understanding of reality, M-theory remains untested. Why? Because it operates in realms of energy and dimensions far beyond our current reach. At its core, M-theory suggests that the universe isn't just made of particles or waves, but of tiny, vibrating strings. These strings, existing in 11 dimensions, could explain everything from the tiniest quarks to the largest galaxies. But here's where it gets even more intriguing. M-theory proposes the existence of membranes or branes floating in higher dimensional space. These branes could be the key to understanding why gravity feels so weak compared to other forces. It might be leaking into our universe from another dimension entirely. The implications are staggering. If M-theory holds true, it could answer some of the most profound questions in physics, like what happened at the Big Bang or what lies beyond the edge of a black hole. It could even reveal whether our universe is just one of many in an infinite multiverse. But for now, M-theory remains a tantalizing idea, a blueprint for reality that we can't yet prove. Which brings us to the next big question. What does M-theory tell us about the ultimate fate of the universe? If it's the key to unifying everything, could it also predict how the cosmos will end? Will the universe expand forever into cold darkness, or will it collapse back into a singularity? The answers may lie hidden in the math of M-theory, waiting to be uncovered. And as we ponder these cosmic mysteries, one thing is clear: the search for a unified theory is far from over. The universe still has secrets to reveal, and M-theory might just be the key to unlocking them. What does the future hold for the universe? It's a question that has fascinated scientists and dreamers alike for centuries. Will the cosmos expand forever into an endless void, or will it one day collapse back in on itself? The answer lies in the mysterious force known as dark energy, which is shaping the ultimate destiny of everything we know. One possibility is the so-called heat death of the universe. In this scenario, dark energy continues to push galaxies apart, stretching the fabric of space-time until stars burn out, black holes evaporate, and the universe becomes a cold, dark, and empty expanse. It's a fate often described as the Big Freeze, where the universe fades into silence, its energy spread so thin that nothing can happen anymore. It's a lonely end, but one that aligns with our current understanding of how dark energy behaves. On the other hand, there's the chilling idea of the Big Rip. If dark energy grows stronger over time, it could eventually tear apart galaxies, stars, planets, and even atoms themselves. Imagine a force so powerful that it rips the very fabric of reality apart, leaving behind a chaotic, fragmented cosmos. This would be a violent and dramatic end, but it's a scenario that some physicists believe could be possible if dark energy behaves in unexpected ways. Then there's the possibility of a big crunch, where the universe stops expanding and begins to collapse. In this scenario, gravity would eventually overcome dark energy, pulling everything back into a single point, a reverse of the Big Bang. It's a cyclical vision of the cosmos, where the universe might be reborn in an endless cycle of expansion and contraction. But will life survive such a cataclysm? Or would it be the ultimate reset button for existence? These scenarios aren't just theoretical musings, they have profound implications for the structure of the universe and the fate of life itself. If the universe ends in heat death, life as we know it would have no place to exist. If the Big Rip occurs, the very laws of physics that hold reality together could unravel. And if the Big Crunch happens, the universe might start anew, but whether life could emerge again is anyone's guess. As we ponder these possibilities, it's worth reflecting on how far we've come in understanding the cosmos. From the mysteries of dark energy to the origins of the universe, we've explored questions that push the boundaries of human knowledge. Yet, for all we've learned, the ultimate fate of the universe remains one of the greatest unsolved mysteries. Will it end in silence, or will it collapse in a fiery rebirth? The answer, like the universe itself, is still unfolding.